In this video, we're going to take a look at example 28-7, and it's going to be in two parts. Part A is going to deal with a half-wave rectifier, and part B is going to deal with a full-wave rectifier. So in this example, we're asked to find the ripple. So if you recall, the ripple is the fluctuating AC component in the rectified DC output. To find the ripple, we need to first calculate what our secondary voltage is. So remember, secondary voltage is equal to the turns on the secondary divided by the turns on the primary. And then in this case, we've got a 4-to-1 step-down transformer, so that's going to be 1/4 times our 120 volts AC, and that's going to give us 30 volts AC. Next, we need to calculate our peak voltage on our secondary. So that's going to be Vs peak, which equals the voltage of the secondary times 1.414. And so that's going to equal 30 volts AC times 1.414. And that gives us 42.42 volts. Now we can calculate our output. So remember, we have this diode in this circuit here, and we're going to get that 0.7 voltage drop, so we need to account for that. So our V out peak is going to equal our Vs peak minus the voltage drop on our diode. So our Vs peak is 42.42 minus 0.7, and that gives us 41.72 volts. Now that we've got our V out peak, we can calculate the ripple. So the ripple is going to equal the V out peak times 1 minus e to the negative t divided by r sub LC. What I like to do to make putting this into the calculator a little bit easier is to go ahead and calculate this exponent, negative t over RLC. So from the print, we know that r sub L is equal to 250 ohms We know that C is 500 microfarads. And since this is a half-wave rectifier, we know that our capacitor is going to discharge at 16.67 milliseconds. Before we plug these values in, we need to do a few calculations to get all our units in the same value. So T is in milliseconds, which is 10 to the minus 3, and our capacitor is in microfarads, which is 10 to the minus 6. So we need to go ahead and convert our time over to seconds. So T is equal to 16.67 milliseconds. Let's convert that. So we need 1,000 milliseconds is equal to 1 second. So milliseconds will cancel out. So that gives us 0.01667 seconds. Okay. And then let's go ahead and convert our capacitance here. So we have C is equal to 500 microfarads. So there's 1,000,000 microfarads in 1 farad. So our microfarads are going to cancel out here. and we're left with 0.0005 farads. All right, so now let's calculate our constant, or our exponent. So we have negative T over R sub L times C. So we have negative 0.01667 divided by our 250 times 0.0005. And what that gives us is 0.133. Next, let's calculate E to the negative, got my sign there, negative 0.133. And that gives us 0.875. All right, so now we're ready to plug in our value of E into our equation. So V ripple is equal to our V out peak, which is 41.72 volts, times 1 minus that 0.875 that we calculated a minute ago. And that's going to equal 41.72 volts times 0.125. And that's going to give us a ripple of 5.21 volts peak to peak. So now, part B, we can find out what our volts DC is, or our average voltage. And this is really what we want to know. So if we have these fluctuations and we need, say, 15 volts for our device, we want to make sure that when we're accounting for the ripple, we still have that steady 15 volts going to power the device. So volts DC is equal to our V out peak minus the V ripple divided by 2. And so since we're only interested in the DC component, or this average voltage, we need to account for the fact that the ripple swings above and below the average. Okay, so we divide the peak-to-peak ripple by 2 and get what we call the DC offset. And we'll get more into that later. So our numbers here, we've got volts DC is equal to our 41.72 volts minus our 5.21 volts peak to peak for a ripple, and divided by 2. And that gives us 39.12 volts.